For the next speaker, we have Sergio Aguilar-Gutierrez, and he'll
Yeah,
talk about entangled universes in the sitter wedge holography. So, Sergio, please, the floor is yours.
yeah, thanks a lot. Thanks, Tales or Nick. But yeah, this I also add a bit extra about the complexity in this model. Uh, because yeah, I'll present something about some previous paper that also was used in order to complete the whole story about the uh, quantum information properties of this wedge holographic model. Okay, so it was done in collaboration with Juan Pedraza, with Ian Kumar, and in this the main paper that I'll tell you about. I'll say something else about the complexity in the sitter that we did with Michael Heller, Silke van der Schuren, and also some recent work with Philip Langdent. Okay, but of course, if I only have 20 minutes or a bit less because of questions, then I'll mostly focus on the first paper. Well, this says about the wedge holography. So, what do we mean by that? Usually, these are like double holographic models where you have some higher dimensional spacetime that is well, there are different implementations. The main implementation was with the way that Takanagi and other people initially proposed this type of models. That is, that is also based on the standard Gauss-Randall models. That you have some higher dimensional ADS space, and then you have some end of the world branes where you can have some type of theories. The modification with wedge holography is that then now they are like a pairs of branes where the intersection between the two branes will be something that is like a double holographic. It has like a codimension to quantum theory that has been implemented in different contexts. The one that we are focusing in this DS wedge holography is when you have some the sitter end of the world branes, and there is some intermediate ADS space in her dimensions that is between the two. Sorry, that is in between the two branes, and there is like a location that is in the intersection between the two branes. They are basically some accelerating universes from the brane perspective or from the high dimensional point of view. Here we have just the Poincaredis, the cylinder, where you can have that these branes will start at some given starting location that in global ADS coordinates is just at minus pi half, and then it evolves all the way to some other location where from the brane perspective is that basically it's from going from minus past infinity to future infinity from some brane observers. Okay, so that's basically the setup. The idea of wedge holography in our case is basically that we have two inner world branes. One is the UV brane, and the other one is the IR. By UV, I mean that it's very close to the UV boundary, and by IR is just is deep in the bulk interior, and the region in between is what we call the wedge. Okay, so this is the type of model that we're considering. This is just instant gravity. We consider that this, from the higher dimension point of view, there is a negative cosmological constant, and we have some pairs end of the world branes with some given tension that will be determining the location of the branes. There are two main cases that we consider in this paper. One where these branes are like in any dimensions, and you basically fix them at some particular location that is just given by the tension of the branes. And there is another that I'll explain you later, where we actually let the brane location to fluctuate. And in that way, we do need to go to lower dimensions in order to get some analytic expressions for quantities that we're interested in. So in this case, we were using these global ADS coordinates, where we have some de Sitter foliations for ADS, and basically this we can delimitate the location of the bulk in the wedge holographic mode between the UV and the IR that we presented with subindex C and V in this particular way. Basically, this you can think about this from the perspective of some Euclidean potential implementation of preparing a state for creating this type of configuration in the bulk. Okay, usually you would like to put some operator in the UV boundary and then in the Euclidean ADS, and in that way you can create some states in that they can propagate into the bulk, and in that way you can create some type of states. But in this type of Hartekokian type of preparation of a state, you can clearly see that the UV brane that is in the right one, and the IR that is this orange will not reach the boundary, so they need to be created by some non-perturbative type of process. In this case, it's just some instanton creation of EPR type of branes. This is how you can think about the preparation of this configuration. And then there is another point that we want to study some information quantities in this type of first setting. So we're basically going to take that one of the branes, the UV, will be very close to the boundary. In that case, then the theory basically becomes gravity becomes basically non-dynamical, and then one can study these information theoretic properties without having to worry about some non-local gauge invariant type of observables. Now you have like a much more control. And we also have some arguments about how this can be taught about some momentum space entanglement between the UV and the IR that actually tells you, based on some previous works, that this will mean that basically you have some factorization between the UV and the IR that will be like the modes that are like encoded between the two type of branes, and then the Hilbert space factorizes, and then one can study sharply about these notions of holographic entanglement entropies or holographic complexity in these cases. So to study that was the setting. Now we want to focus on what we can learn about this in order to get some lessons for the Sitter holography, basically from the ADS perspective. So we can use this HRT formula that basically tells you about how to relate some entropies in terms of some quantum dual to some gravitating theory. And well, first we specify what type of entangling region we want to consider where we can do the measurements of some quantities. So we specify this R using this the Sitter global coordinates for the embedding that we have, like ADS that they can be foliated into the Sitter slices. Here we are using that this R has to be some global. Well, it's actually okay. This is a typo. Here I'm using the Sitter slices and using this global de Sitter time instead of the global ADS that I was using in the other slices. Then this R is basically just some interval. This is for convenience. This makes the calculation basically much easier. I'll show you how this looks in some pictures. It's just some intervals in this type of foliations. This is like the some maximal and minimal values for the angles, and then we're looking at different global time slices. Then we can think about this is basically some observer that is in the UV on the UV plane. Then this is the natural coordinate system that they will be measuring in global de Sitter coordinates. And then we can think about this these HRT formulas, how we can implement these notions of entropies in respect to this UV observer that's close to the boundary, using just some geometric notions in the bulk, using some dimension 2 surface areas that are like homologous to R. So this is basically how they look like. Again, this is a typo, sorry about that. But yeah, no, this is fine. So here we have some foliations. Well, some global time slices in global ADS, where you can see about the locations of the different branes. Yeah, so we're basically fixing that this region in black, there is R, will be the entangling region where we we're making the measurements when we are like computing the entanglement entropy for some reduced density matrix in R from this whole slice that is in the UV brane. And basically here we can have different type of phases for the entanglement. One will be like some surface that we here we are calling it disconnected because it is like only connecting the UV, but it doesn't connect the UV with the IR. And there is also some connected phase that basically goes from the just from the quasi boundary to the location of the IR brane, where we are integrating out some degrees of freedom. So basically these are like the two cases. There is another one where this interval R is large enough that it basically also covers some region in the interior of the IR brane. When that happens, then you also need to take into account that then there is like some maximal number of degrees of freedom encoded in this IR brane, and that has to be implemented also when you're doing the calculation of the maximal area surfaces. Then if you have like a multiple saddles, because now you have like a disconnected and a connected phases, then basically the entropy that will dominate in the calculation is the one that is given by the minimal between the two cases. Then this is what you can find about the notion of a Pesch curve. Obviously here I skipped some details about how you can do this calculation, but yeah, in principle is very straightforward. Here I'm just plotting the different entropies you can find. This is for simplicity in the three-dimensional case that you can recover this plot. You can in principle recover something very similar when you're talking about the hard-dimensional cases, and then there is some phase transition at some particular time. Basically, you can find that this phase transition is always occurs before the disconnected phase actually reaches the IR branes. And then there is an interpretation that now we can see that there is some island phase that is basically the one that is connecting the two branes, that they will represent some connection between the UV and the IR locations of the modes. And this is also related to some previous work about the momentum space entanglement between different spaces okay. In principle, was using some free theories, but it also has some generalization with the interacting mass. Okay, this is the second part of the talk that is about the complexity. Basically, we study like a different codimension one type of observables that we're calling that there are like many hints that they may have some representation from complexity of some quantum circuit that might be dual to some other notion of that we're calling like a holographic complexity in the bulk. And then this is the particular type of observables that we studied in this case. This is called the sequel to anything proposal for codimension one observables, where this sigma epsilon, where this epsilon, I'll show you how does it look like. Basically, are surfaces where you are evaluating complexity. Okay, great. and then there is like some particular region of where you are like fixing these two slices. They represent basically the future in the past of some particular slice. Here you can see how this looks like. Basically, here we have the UV and the IR branes, and in between we have the global ADS. There is some bulk region that is delimited in the past and the future by these two slices, and basically we want to define this location of these particular slices using the extremization of some function. In that way, you can have a covariant notion of some observable, and you can find that the extremization for this type of sum of weights of different codimension 0 and codimension 0 and codimension 1 volumes basically tell you that the extrinsic curvature of these slices has to be some constant that is given by the particular weights that we're using. Okay, so this evaluation is in principle very complicated if we are talking about the particular case that we consider. Basically, you need to use some coordinate system where you can do the explicit evaluation, and it becomes tractable. But yeah, for this wedge holographic method, it's still cumbersome. Then the simplest case that I'll present you, but you can see, of course, more details how this gets more involved in our publication. The case I'll tell you is about when the IR and the UV are close to each other, and basically that's where you have just they're basically just considering complexity in the de Sitter slice, in the de Sitter brane. So you're not worried about some corrections due to the intermediate bulk space. Okay. Yeah. So. This is also based on some, this pair is based on some previous work on the Sitter complexity that I'll tell you a bit more about. But basically, you can find that there is like some, using this type of codimension 1 observables, you can see that the evolution of complexity basically obeys this type of evolution. It goes from some point where this some rapid growth of complexity according to that type of observables that as you increase like the extrinsic, the mean curvature of these slices, this growth can be layer and layer, basically because of how geometrically you can see how this is implemented in that case. Then you can also study what happens when you increase the values of this mean curvature. There is a point where this actually, instead of reaching some hyperfast growth of complexity, basically when the derivative goes to infinity, there is instead some critical value of the mean curvature where this slices simply, where the complexity simply grows linearly with time. And then you can derive some relation for that. I can tell you some technical details if anyone is interested. And then we also propose some way that we can implement some covariant notion of this linear growth of complexity, that you also have some expectation based on quantum circuits. And then here you can see our work where this was first proposed, and we also applied this in the wedge holographic method. So this is just to wrap up. I'll tell you very briefly about this. You can also study what happens when you let the brane fluctuation to the brane location to fluctuate with some scalar modes, and then you can find that the higher dimensional from 3D gravity in the bulk, you can see that the two-dimensional effective description of these fluctuations is described by the Sitter JT gravity. We also propose some multivariate small based on the lower dimensional cases, and this was with Philip. That was that I can explain you what we mean actually with that. But yeah, since I see we are running out of time, then I'll just give you some brief summary. Then we studied this notion for testing quantum information concepts in the theta space with the ADS-CFT dictionary. We studied that there is some emergence of island phase transitions between the UV and the IR. There is this notion of complexity proposals where some of them has hyperfast growth and some of them has latent linear growth. And then there are other interesting application for lower dimensional gravity that you can study. Okay, thanks you.
All right. Thanks, Sergio. Thanks a lot for the talk.